Hello, we are here again to talk about complex networks. Today we will discuss about static and dynamic models, as we see that models are very important tools in this field. Why we need to use network models? Because they help us to understand the networks in a very deep way. It is possible to take clues about the past of the network. We can do a regression of the network, and it's possible to foresee the future of the network. It's possible to do projections about the structure and the behavior of the network. And furthermore, it is possible to measure directly statistical properties in several realizations of a network model in the case where analytical solutions are not easy to do. Usually, new proposals of the network are based in models. We propose a new model of network, and this model will help us to understand some real problem. But what is a network model? A network model is essentially a construction recipe. We have instructions to do one new network. And this recipe informs us about the order, the size, and the way the nodes are connected among themselves in the network. We can include expected properties of the network in the model. Then, essentially, a recipe. How I will build a new network. There are two types of models, the static models and the dynamic models. The static ones are models that reaches a static final state of the network. It is, I will follow the recipe and I will prepare a final state network. The network, once done, is finished, is my final product, and I will not change anymore this network. Then there is no temporal evolution of the network. Once the network is finished, I stop any changing it. There is no correlation between the model procedure and the portrait phenomena. It is the way I use it to build the network is not related to the problem. I can, for instance, do a random connection around the network, connecting randomly the nodes with some neighbors. If the model is suitable for me, it not means that this was the process that occurred in the real world. It was the process that I used to do my network, not the problem itself, okay? And we can use static models as well to map phenomena. Then I will get a map, and this is a static model because it is like a picture about the problem. I take a photo of the problem. It's a map. It's static because I will not change this map anymore during the research, okay? Dynamic models doesn't reach a final state. It means that the network, according to this type of model, will grow along the time. Then I will start from an initial state, and I will grow and grow and grow and grow the network until I reach a state that is suitable for me. But the model will not impose a final state. Then there is a temporal evolution in the network. Because this temporal evolution, I can back in the process and take clues about how was the network in the past, and in the same way, I can follow the process and foresee the future of the network. Because I can do this movement in the time, uh, it must be some correlation between the model and the problem, because they run along during this process. If my process is random, I will not reach the evolution, the temporal evolution of the network. They will not match with the real situation. The evolution will not match with the real situation. Dynamic models, because it is type of characteristics, are sophisticated models, more sophisticated than the static models in general. Well, in summary, static models are recipes to a final product, a final network that will not change when it is done. And dynamic models are models, sophisticated models that grow the network along the time. Okay? One of the first network models was given by Erdős and Reni. It is similar to the model proposed by Solomonoff and Rapoport, and it is known as random graphs or Poisson random graphs. This model was developed in 1959, and it was very important because in some way it started the complex network areas. But in that time, the model was proposed only as a mathematical tool, not for real problems. The Erdős-Reni random graph model is a recipe to construct several realizations of the network. And we have two different procedures to do it. They will reach the same objective, to construct a network. In the first case, we start with the number of nodes we want in the network and the number of edges we want to put in the network. In the second case, we start with the number of nodes we want and the probability of the connection among the nodes in the network. It is only a matter of preference or suitability for a certain problem, because at the end we will reach in similar objects. In this slide, we can see the set of nodes in the first down at left, and the probability is 0. Then I will not connect the nodes. It is the same as using 0 as the number of edges in the network. In the middle of the screen, we can see a sparse connected network. The probability is about 1/10. It means that each node is connected with its neighbors with 1/10 of a probability. And the last picture shows a slightly more dense network where the probability is 0.2. Then we can generate the network starting with a fixed number of nodes and the number of edges we want to put randomly linking these nodes, or the probability to link the nodes. It is the same in the end, but you can use the best solution for your problem. A very interesting thing about the Erdős-Reni model is the model is very well studied. Then we have analytical solutions for several of its properties. For instance, we know how many nodes, how many edges. We have a lot of information about the network, even if we don't build the network itself. We can do it analytically. In this slide, we can see that for a network of 10 nodes, we can think about 3.5, 10 to 13 combinations of edges. It's a very good number. And we can calculate the expected average degree as we do in the second part of this slide. And for a network of 10 nodes and the probability 0.4, we have an expected average degree about 3.6. Then, it is easy to do calculations in StaticDynamicModel because the equations are already, because a lot of decades of history. Okay, we see in a chart the behavior of the network as we increase the mean degree. You can see that a giant component appears in the network, and at the end, at the limit, will get together all the nodes of the network. Then it is a transition process, a phase transition process, or percolation process, if you prefer, that occurs in this type of networks according to the mean degree of the nodes. But remember, R2N is a static model, then it's not a time series evolution, okay? You define a network with mean degree of 4, for instance, and you will find this size of a giant component. You are not evolving the network, growing the network, okay? It is a static model. Some characteristics of R2N realizations. The networks are small world networks. They are not scale-free. They have a low cluster coefficient. There are two triangles in the network. The model is not good for real problems. It started with a mathematical tool, not a model for complex networks, but still, it is a good model and a simple model. After R2N, we saw in the literature the configuration model. The configuration model uses a series of degree sequences as input parameters. Then we create a series of copies of some vertex E according to the degree of the vertex. We link randomly the vertices, one link for each node, and we combine the copies of each vertex in only one vertex. This model, the configuration model, produces networks with loops and multiple edges. But the configuration model is somewhat artificial. It's difficult to find a real problem that matched well with the configuration model. Okay, we can improve the parameters, the process, to match our problem. But in general, it's not so easy or not straight. Another very successful model was the model proposed by Watts and Strobitz. And this model is known as small world networks. Small world because we have small patches in a network, in a big network. It is something like if the network grows linearly, the size, the length of the patches inside the network will grow about logarithmically. Okay? Then, if I have a very big network, I will find small patches among any nodes in the network. Okay? This is the idea of a small world. I have the big world, but the patches are small. And StaticDynamicModels proposed the recipe where I start with a regular lattice, we can see in this slide, and in this lattice, each vertex is connected with its neighbors, we can see here, up to distance k. Then, for instance, distance 1, distance 2, or in the drawing only distance 2. With a probability p, we change one end of each edge, taking it to a node uniformly chosen. Then I will rewire, it's the name of the process. I will rewire the network, changing the endpoint of the edges according to some probability. Okay? In the process, we start with a regular lattice, a regular network, not a complex one, a regular network, and we step forward to a complex network. In the middle of the process, we will reach to small world networks. If you follow the process and follow more and more, you will reach something like the random network, because the number of rewires will produce the random effect in the network. Then, in general, we stop in some point in the middle between the regular and the random network. Okay? StaticDynamicModels model is very interesting because it brought to discussion the small world effect. Remember, StaticDynamicModels is a static model. Then, when you stop the evolution, you get your network. The process is to build the network. Okay? During the process, you are constructing, you are building your network. And at the end, in some point of this line, you stop and you get your product, your final network. After that, you will not change the network anymore. It is a static model. Here in the graph, we can see the behavior of some of the measures of the StaticDynamicModels networks realizations. Now we will talk about the price model. It was developed in 1965 and it gives support to the growth of the network or the evolution of the network, temporal evolution. Okay? We can find here cumulative advantage effect. It is some of the characteristics, mainly the node degree, will improve, will increase along the time. And the oldest nodes will have more of these characteristics or benefits. Then, if you think that a large number of neighbors is an advantage, this is a cumulative advantage because oldest nodes have more time to get more and more neighbors. Okay? Price model is about didactic graphs and generates scale-free realizations. But this model, I think, didn't receive the enough attention in that time. In the graph, in the charts, you can see the difference between random distribution of degrees. It was produced, for instance, for an Erdo-20 WASP, and here in log-log scale, the degree distribution of a scale-free network as provided by price model. Okay, it is very difficult to represent this graph in a linear scale. Then usually we put it in the log scale. In the same direction, in 1990, Barabasi and Heka Albert proposed a network model. It is now as Barabasi Albert model or scale-free model, but Price has scale-free properties in this model. Barabasi Albert model was very successful and it started a very high interest in the field. The model has a better representation of a wide range of phenomena if we compare with random configuration and the Watt-Strobel model. Okay? Then, Barabasi Albert, a dynamic model, is a better representation for a lot of well problems if we compare the model with the previous ones. Network model, okay. Barabasi Albert networks present hubs. Hubs are very connected nodes in the network with an average degree higher or very higher than the other nodes. Barabasi Albert model is suitable for undirected graphs and generates a single component network. Then there is no isolated nodes. There are no isolated nodes or isolated components. It is interesting because there is a patch between any pair of nodes in the network. Okay? And the recipe of Barabasi Albert is you create an initial network with connected vertices or connected nodes. From this start, from this core, new nodes are added with a fixed number of edges. The edges are connected preferentially to the highest degree vertex. Okay? This is the preferential attachment property, or in this case, preferential attachment direction. Okay? There are a lot of generalizations and modifications and the new proposals starting from Barabasi Albert model. We have a small list of authors that proposed a new model. For instance, when we change the probability of connection of new vertices, including a K0 negative. Okay, this is a different recipe, similar to the original but a different one. We will finish with different networks. Okay, in the same direction, changing the original model of Barabasi Albert, Kaplinsky and others proposed changes in the probability of connection of new edges, bringing the distribution to the non-linear probability. And it may reproduce linear scale if we have 1 as the exponent here. If you change this exponent here in this this relation, we will change the condensation of network. Then, each new model um, from Barabasi Albert, the original one, will change some properties of the network, but essentially they keep the referential attachments and the scale-free degree distribution of nodes. Okay? Here we have another situation. Dorogovitsev and Mans propose changes in the average degree of new vertices. While the network is evolving, the new nodes arrives with each time more and more edges to be connected. The average degree of new vertices is increasing in the time. This is the idea. This model is a good reproduction of a real network exponent. Talk about exponent because a lot of real problems are well mapped by scale-free networks, and the exponent is the main parameter to understand the statistical distribution. Okay, but Parabas-Albert model and it is following models are only one family, we can say, a family of models. Okay. For instance, we have here the vertex copy model because the others are not so suitable for biological phenomena. Then we can see in this slide a model that is suitable for genomic studies. Here we change the connection procedure of the edges. Starting from initial core, the connection is handled or it copies connection of existing vertices. It is, I get a network in a suitable state, then I will connect nodes. It is the main part. I will connect nodes and I will choose between handling connecting the nodes, or I will inspect one existing nodes and I will copy that connections to the new configuration. In this case, the model allows the removal of vertices and edges. It thus appears in the VA mode. We have some classes of models, and one of these classes is geographic models or geometric models according to some authors. Network models that are geometric or geographic are based in the condition that the network is embedded in some physical world, some physical framework if you prefer. Okay? Then this framework, this physical reality will change or will impose constraints in the network. There are classes of models. Okay? We saw several of them until now, and I will talk about a network model I developed some time ago. This is a geographic or spatial or geometric model. It depends on the author. You see these different terms to say that geographic models or spatial models are models that consider some frameworks, some physical frameworks, some restrictions, some constraints over the networking, usually the networking growth. Okay? Then, in this model, we take care of the position of nodes because we are trying to map or to understand the evolution of computer network around the country. Then the position of the cities, the hosters, matters. Our model was designed to emulate the internet growth, and it's applicable to other geographic networks. It's important to note that the position of the nodes is an important information. I can't change, I can withdraw the network, change the position, because the position is a part of the WASP2 is a network. Our spatial network has the same. The position is important, it's part of the process, okay? And this position will impose some conditions to the network. Here we have the WASP of my model. We define a physical space. We add the first network node in an arbitrary point, and each new node is placed in a random position, but this position is important. It's random because I'm putting new nodes, but once I define the position, it can't be changed, and it connects to the closest existing node. This model mixes long and short patches, and the length of patch is correlated with the age of the node. Okay? In this class, we saw complex network models. Models are a very important tool in complex network field. We saw that there are static and dynamic models. Static models usually are simpler than the dynamic ones. They give us a recipe to build a network realization, and when we do the realization, we fix it. Then we have a final static network. Dynamic models are the opposite. They give us a recipe to evolve a network, starting with a given state, and we stop the evolution when it is good for our proposals. Okay? Then we can see the future and the past of the network according to our interests. After the conceptual explanation, we saw some very known models, starting with the random model from Erdos and Henning. We saw the configuration model. We talked about Watt-Strogatz model, Price model, and the very successful model of the Barabasi and Albert. After that, we saw some other models, and we passed through the fact that there are some models that incorporate more information, as is the case of the geometric models that embed some embed the network in some framework, in some physical reality. Okay? It is interesting to know that if you want to study networks and your problem is not matching with the known models, you have the freedom to propose a new model of network. It's a very interesting, very good, and very exciting area of research, the proposal and the validation of the new network models suitable for specific situations. Okay? Thank you for the attention.